This is example 1124 from the textbook, which shows how to use eigenvalue and eigenvector techniques to solve problems involving Markov matrices. So the way Markov matrices work is if you have a population that's undergoing some kind of dynamics, where there are transitions from one state to another state, and there is a conservation of the total population, then that process can be described by Markov matrix. So in the textbook, there's an example about people moving from one state to the other. So we have Maryland, Pennsylvania, and Delaware, and there's a flux from one state to the other every year. So let's suppose if I look at the people going from Delaware to Maryland, let's say that 20% of the population every year of Delaware's population, 20% of them move to Maryland, 8% of them move to Pennsylvania, and that means that 72% of them will stay at home. And then we can look similarly at the people going from Maryland to Pennsylvania. Let's say that 10% of the population of Maryland goes to Pennsylvania, 12% goes to Delaware, and then the remaining, what would it be, 78% stays home. Then from Pennsylvania, we have, let's say, 3% go to Maryland, and 10% go to Delaware, with the remaining 87% staying home. Okay, so we can describe that process in terms of a matrix. So every year, the new populations. So let me call this Delaware, Maryland, and Pennsylvania. I'll write those in the form of a vector, and I will put a little prime, which means in the subsequent year, that is going to be equal to the so the people going into Delaware. So 72% of the people who are in Delaware stay there. 12% of the people in Maryland enter Delaware, and 10% of the people in Pennsylvania enter Delaware. So if you look at these guys, the 72% is stay at home. The 12%, those are the people that are coming from, I'm sorry, I forgot to draw my arrowhead. Those are the people coming from Maryland into Delaware. And then the 10% over here, those are the people coming from Pennsylvania into Delaware. Okay, and then similarly, we can figure out how many people are entering. So those again, those are the people coming from Delaware, Maryland, and Pennsylvania. And we can do the same thing to find the people entering Maryland. So the people coming from Delaware into Maryland, if we look at that, from Delaware into Maryland, that's going to be this 20% right here. So that's 20% of the people that are in Delaware are going to be entering Maryland. And how many people are staying at home? 78% of the people in Maryland just stay at home. And then 3% of the people in Pennsylvania go to Maryland. Finally, we can look at the people entering Pennsylvania, and then we have 8% of Delaware, 10% of Maryland, and then 87% of Pennsylvania are going to come in. And so if you look at this so-called Markov matrix, where you have a population and the total number of things stays constant, there's just flux where things are moving from one place to the other, we have each of the columns adds up to 1, right? So 72% plus 20% plus 8% is 100%. So we've got 100% in that column. We've got 100% in that column, and 100% in that column. In a matrix with this property where every column, all the numbers are positive, every column adds to 1. This is called a Markov matrix, and it represents some process like this where things are flowing from one state to the other. State could be literal in this case, like states in the Union. Okay, and so the question is, after some number of years, what's the population? And so so if I want to find the population in let's say this year is 2018. If I want to find the population in 20 19, well, that's just the matrix. Let's call it curly M to distinguish it from Maryland. So curly M is the matrix. So this would be curly M acting once on the 2018 populations. So D, M, P as evaluated in the year 2018. If I wanted the 2020, so D, M, P in the year 2020 would just be, I have to advance by one more year. But in 2019, it was just M times the 2018 population. And so you see what's going on is that every time we want to advance the total populations from one year to the next, we have to multiply the population vector by the Markov matrix. Okay, and so the point is that it's very convenient in situations like this to think about the eigenvectors and the eigenvalues and decomposing things into the eigenvectors and eigenvalues. And so we talked in class about the arithmetic to do that for a matrix like this. We can just plug it into your favorite symbolic algebra package like Mathematica or a numerical package like MATLAB, and it will tell you that there is an eigenvalue, the largest eigenvalue is 1. And so for Markov matrices, you will always have an eigenvalue equal to 1, and then the associated eigenvector, which we'll call E1, is going to be proportional to negative 0.56, negative 0.62, negative 0.82. That overall negative sign is completely arbitrary, and in general, the overall normalization of an eigenvector is arbitrary. So in this case, we don't have to worry about the value of alpha or these negative signs, but the ratio of any pair of those entries is what's really important. And so we can do the same thing for lambda 2, which turns out to be 0.77, and then the associated eigenvector for that guy is equal to minus 0.09 minus 0.70 and 0.79. And then finally, for the last eigenvalue, we have the eigenvalue is 0.60, and the eigenvector is minus 0.62, 0.70, and finally minus 0.07. Okay, and again, the overall normalization of these is arbitrary, so if you use a different package, you might come up with different overall scalings of this vector, but the ratio of the coefficients is always going to be the same. So then the question is, what good will all of this, what good will all of it be, and what do we use it for? Well, let's suppose that we want the population after 5 years. Okay, so let's say D, M, P, and let's just use this year as year 0. So we want the population at year 5. That's going to be M to the 5th, because we have to advance the population vector from one year to the next 5 different times, D, M, P, now, today, this year. Okay, so we could simply multiply that the population vector 5 different times by the M matrix. That would be fine if we had a computer at our disposal and we didn't want any more insight. But what I want to argue is that it is very convenient to write the state vector in terms of the eigenvectors. So that's the key idea. So writing the state vector, or writing the population vector of the eigenvectors, simplifies the analysis and arithmetic. Okay, so for instance, if I write the population, well, let me write this as DMP. Today, if I write this in terms of the eigenvectors, so let me write this as alpha 1 times E1 plus alpha 2 times E2 plus alpha 3 times E3. Let's see what happens now when I multiply this on the left with the Markov matrix to advance it to the next year. So DMP in year 1 is DMP in year 0 times the Markov matrix. But if I write that in terms of the eigenvectors, Bm acting on alpha 1 E1 plus alpha 2 E2 plus alpha 3 E3. Okay, so this is linear algebra, which means that the matrix multiplication distributes, and I can write that as alpha 1 times m acting on E1 plus alpha 2 times m acting on E2 plus alpha 3 times m acting on E3. But I know that since those are eigenvectors, this first guy is going to be alpha 1. This is going to be 1 times E1 plus alpha 2 times lambda 2 E2 plus alpha 3 times lambda 3 E3. Then, if I want to go to the next year, DMP2, which is DMP1 pre-multiplied by the matrix, that's going to be m acting on our previous result. And again, since it's expressed, since that population vector is expressed in terms of the eigenvectors, what happens is that every time the matrix M acts on one of the eigenvectors, E1, E2, or E3, I simply get one more factor of the associated eigenvalue, and that is the key. That is what makes all this analysis in terms of the eigenvectors much simpler than the analysis in terms of the original naive population vector. So I have an alpha 1, I have an alpha 1, then I have 1 squared, also known as 1, times E1 plus alpha 2 times lambda 2 squared. I have another factor of lambda 2 because I've hit that E2 vector with the M matrix one more time. And then finally I have plus alpha 3 lambda 3 squared, sorry, I missed my E2, E3. And great, and so in general, if I want to get out to the nth year, I have that population, Delaware, Maryland, Pennsylvania, in year n is equal to m n times, I'm going to act on that vector, DMP0, but that's equal to, if I write things in terms of the eigenvectors, it's going to be alpha 1 E1 plus alpha 2 lambda 2 to the n E2 plus alpha 3 lambda 3 to the n E3. Okay, now let's go back and look at our example of the Delaware, Maryland, Pennsylvania populations. And if we look at the eigenvalues, lambda 1 is 1, lambda 2 is 0.77, and lambda 3 is 0.6. And so notice those guys are all less than 1 except for lambda 1. So what this means is that as n goes to infinity, if I look at these terms, lambda 2 to the n is going to go to 0 because lambda 2 is less than 1, and lambda 3 to the n is going to go to 0 because lambda 3 is less than 1. And so the whole population is going to tend to just E1 times alpha 1 as n goes to infinity. So what we've shown, thinking about things in terms of the eigenvectors, is that, especially for Markov matrices, the special eigenvector that has eigenvalue 1 is called the steady state. And what happens is that in the limit of a large number of iterations of this Markov matrix on the population vector, all the components of that vector along E2 and E3 will eventually go away because of these factors of lambda to the n that appear on them. And you'll only be left with that initial contribution from the first eigenvector. Okay, so I hope this has been a clear demonstration of why it's convenient to use the eigenvectors in certain kinds of problems, this being an example of a Markov matrix.